Okay, so we'll continue the previous topic and we'll talk about 2D Poisson equation with boundary conditions. So last time we ended with the following statement that if we have some domain D, we have a green function that solves this equation. With zero boundary conditions. Then a solution to another boundary problem without right-hand side, but with non-trivial boundary conditions can be given in terms of the same green function. So in the same. Oh, sorry, it's on the boundary. Yes, it's not zero identically. So if we have a problem like this, Poisson of u equals to 0, and u restricted to a boundary, a solution to this problem is given by this formula. U of 0 is the integral over boundary dn gradient of g z0 times u0 of z. So this other green function that gives us the solution to this problem is described by derivative of that green function, and it's always like this. Like there is a main green function that depends on 2 points inside the domain, and all other green functions can be expressed in terms of this one. And we started to study the following example of this phenomenon. The upper half plane. So this is our domain D. This real line is a boundary of D, and so there is some point 0. And can you remind me the formula of a green function in this case?
Zeta minus zeta 0
over
zeta minus zeta 0 conjugate.
Thanks.
In absolute value.
Yes. Thanks. So it can be obtained as a ratio of this well, as a combination of potential created by this charge and its mirror image. So this absolute value of z minus z0 is a distance to point z0. This is z0 bar, and this is the distance to z minus z0 bar. So if you take the ratio of these two distances computed on the real line, then they're equal. So this argument of logarithm is 1 when we are on the real line. So this gain function vanishes. And now we want to see this other gain function. So uh, integration along the boundary goes in this direction because it is kind of counterclockwise standard orientation. So integration over the boundary goes in this direction. Normal to the boundary points to this direction. Probably I might miss some of orientations which can produce the opposite sign, but we will see if it is correct or not. If not, then we will simply change it manually. So we want to compute this other gain function, which we can call G1 is G1 is n gradient of G. So it depends on Z0, Z0. So it equals to minus y derivative of this gain function with Z placed on the real line. So we write that Zx is x plus Iy. Oh, this gain function is minus dy logarithm of x plus I y minus 0 x minus I y minus 0 bar uh, 1 over 2 pi. Oh, so probably I should have used this space. It's fine, I don't want to move this formula. And then we should also put y equals to 0. Maybe. So this is a contribution from the numerator. Logarithm of this variable plus logarithm of its conjugate. When contribution from the denominator. Like this. So let's differentiate this. So be I over x plus ay minus z0 minus like this, and now we can put y equals to 0. So these two terms combine. No, not. Wait, did I make a mistake? Let's check. Wait, why did I put here x minus iy? It was x plus iy. Sorry. Oh, this is x plus iy. And okay, was minus sign. And this is, yeah, now it should be fine. Yeah, so these two terms coincide after the substitution. These two terms also coincide. So we get 1 over minus I over 4 pi. And d and dy is not needed. Yeah, so we have this expression. Now I also want to write this z0 in terms of real and imaginary part, because we want to study this again function in the asymptotics when imaginary part of the 0 goes to 0 when we approach the real line. In this case, we see that this again function will go to 0 because the 0 will approach the 0 bar, and we would like to see this phenomenon. So let's write this as x minus x 0 minus I y 0. So this expression, and now let's combine them together. Sorry, 4 pi turns into 2 pi because they were identical terms. So turns into 1 over pi y0 over x minus x0 squared plus y0 squared. So do you recognize anything in this expression? Yes, yes. And so it's delta x sequence with parameter y0 and argument x minus x0. So we see this formula that a solution to our boundary problem is the following. U of x0 y0 is given by the integral from minus infinity to plus infinity d dx delta y0, this particular delta y0 of x minus x0 x0 u0 of x. So in particular, when y0 goes to 0, uh, u of x0 y0 goes to u0 of x0. That happens for delta x sequences by definition. So we say that this solution actually satisfies this boundary value problem, and we also see that it is indeed a solution because this function is a combination of holomorphic and anti-holomorphic one. So each of them is killed by a Laplace operator. And one small remark that since we are working in this domain, which is infinite, this boundary condition, the green function at the boundary equals to 0, should actually be specified for infinity. It means that this green function should be finite. It should go to 0 when we go to infinity in some other direction. Like there is one point at infinity, and we should ask this green function to vanish there. So. Because if we remove this condition, we could in principle add some expression like imaginary part of z, which goes at infinity, and still solves the Laplace equation. So such a condition should be added if we work with infinite domains. So it's equivalent to requiring g equals to 0 at the boundary. So are there any questions about this? By the way, let me also show you another way to obtain the same formula. Because almost any problem has at least two different solutions. So using the Fourier transform. So they are probably the same. That well, I'll not write it here. I know, probably let me write it. So u of x u of x 0 should be u0 of x, and a Laplacian of u of xy should be 0. And also u of x y go to 0 when x squared plus y squared goes to infinity. It should be regular at infinity. So if we want to solve this equation, we can perform partial Fourier transform. In the x direction of u tilde of ky is integral from minus infinity to plus infinity e to I k minus ik x u of x y dx. And the same for u0 for initial condition. So, and can you tell me what equation is satisfied by u tilde of k and y?
The second derivative minus second derivative equals itself.
Second derivative in what?
Okay.
No. It was originally second. There were originally second derivatives in x and y. How do they transform to second derivative in k? So, yes. So minus k squared u tilde of ky equals to 0. And then there is boundary condition that u of k u tilde of k 0 equals to u0 tilde of k. And there is this last condition, which is important, that u tilde of ky goes to 0 when y goes to infinity. Plus infinity in our case, because we are working in the upper half plane. And who can solve this system of equations? Who can write u tilde of k and y? So k plays a role of parameter in all these equations. So the real variable if you solve all these equations is y. So I can write it like this. And there is this set of ODs for each for each value of k. But
It's no reason for some combination.
no, because well, in a sense, we can call them sines and cosines, but if you compute second derivative of sine, it is a minus sine of x, and cosine minus cosine of x. So there are better functions in this case. Hmm? Uh, yes. But the question is, are they the functions that we really need? Because a hyperbolic cosine is cosine of what? Of y is e to y plus e to minus y over 2, and hyperbolic sine e to y minus e to minus y over 2. So they behave like this. They grow exponentially in both directions. So it's of course they don't look precisely like this, but idea this idea should be clear. In the sense they have growing exponentials both for plus and for minus infinity. And this contradicts our requirement that the solution should be regular at infinity. And it's better if it even goes to zero. If this boundary condition also goes to zero at plus and minus infinity. So, what?
You zero k times e to the minus ky.
Yes, almost. So let's first write this formula. So it's pretty close to the correct one. Hmm?
So over e to the minus k.
What do you mean?
Well, divide.
Like this?
Yeah.
Why? What does it mean?
So when y is equal to zero. Sorry,
Mhm.
sorry. No.
Yeah.
I confused
Mhm.
y equals to 1.
Mhm. Yeah. There is one problem with this formula because k can be either positive or negative. So this equation has two solutions: e2 plus ky. Hmm? Hmm? Yes, thanks. So we see that this function for that's for a image for arbitrary y is given in terms of boundary condition by this kind of formula. It is somewhat similar to the solution of the heat equation with the initial boundary conditions, but this function is different. It is linear in k, not k squared t, but it's also similar in the sense that we have some function for y equals to 0, and then it becomes smoothed by this multiplication by decaying exponential in the Fourier space. And as we know about the Fourier, about properties of Fourier transform, if such an equality holds for Fourier images, then what can we write about functions themselves? So what can we write about this function u of xy and function u0? How are they related? So there is this function is also for an image of something, and that function is precisely delta y. So we know that the integral from minus infinity to plus infinity dk e to minus absolute value of k y e to I kx is precisely that delta x sequence, delta y of x. We computed this before. We can compute it again. But so if we know this, what can we say about this function in the coordinate space?
Maybe it's like a convolution.
Yes, thanks. So then u of k y is a convolution of delta y times u0 of u of x y of x, which is precisely this formula, right? Written there. So it is integral from minus infinity to plus infinity, and dx dx prime, for example, over pi like this. Oh, we are covering the same expression. Are there any questions about this computation? Okay, so let's go further. So we kind of know everything about this domain, about the upper half plane. We also know about the circular domain. But I would like to say that the story is similar for any two-dimensional domain that is well, that is topologically a disk. The only question is so. The only question is how to map this domain into the upper half plane or into the unit disk. So if you want to solve a Laplace or Poisson equation in the arbitrary domain, we need to map this domain to the upper half plane. And such maps are called conformal maps. So mm, all this works like this. So suppose that I have some domain D, and we have a coordinate that parameterizes this domain Z. And suppose that we have a map described by a function W of Z, which is a complex analytic function. Uh, since its d-bar derivative is 0. And suppose that we know this. So this function maps us to the upper half plane. And we'll see several examples of such functions. But so far, let us think that it simply exists. So this is our domain. Uh, and this coordinate can be called W. If there was some point Z0 in this domain, then this point maps to W of Z0. Uh, and the question is, can you propose some function that would solve Laplace equation with delta function on the right hand side on the left? So we already know this formula for the upper half plane. Can you try to guess such an expression that that satisfies the Laplace equation of G, it is called GD of Z0 equals to delta function of Z minus Z0 and GD of do you have any suggestion? So you can use the function W to do this.
Sorry,
Hmm?
we know that the point zeta 0 near the boundary are mapped near the real line.
Yes,
By boundary.
yes, of course. So this picture means that this boundary maps to boundary, and then if you go inside, so there will be some point that maps to infinity. This upper half plane is a kind of compactified. And we'll see such a map for one simple example when this domain is just a circle, which we already know. So there will be some point that maps to to infinity. So it breaks at some point. So W of z infinity is infinity.
So maybe we just compose W with G.
Yes. So yeah. So we can write a formula like this. Z0 is 1 over 2 pi logarithm of W of z minus W of z0 divided by W of z minus W of z0 bar. And that's it. Because first, actually, so this map should also be one-to-one. It should not glue different points together. So if 2 points in the image coincide, then 2 points in the image are also the same.
And the inverse is also analytic.
Yes, of course, because it can be inverted locally.
Okay.
Yeah. So to check that everything works, we need to check actually just a few things. So first, if z is different from z0, then this green function is a combination of 1 over 4 pi logarithm of w of z minus sorry, probably here I should have indeed started here. So if z is different from z0, then this green function is a sum of homomorphic and anti-homomorphic part. So this is scaled by d bar, this is scaled by d. If I'll probably erase this because it will not be used in all this complex analytic story. So zero everywhere except this point. When z approaches the zero, then this can be expanded as 1 over 5 logarithm of W prime of Z of Z0, Z minus Z0 plus something else divided by W of Z minus and W of Z0 minus W of Z0 bar. So as a function of Z, it is 1 over 2 pi logarithm of absolute value of Z minus Z0. Absolute value Z minus Z0 plus some constant. So it has the same singularity as an ungain function in the free space. So Laplacian of this GD is a delta function Z minus Z0. And the last part, if we need to check its boundary conditions. If Z lies on the boundary, then the imaginary part of W of Z is 0 because it is mapped to upper half plane. This is the real line. Or it is the same as to say that W of Z is W of Z bar. So our gain function G in the domain D Z ZR is well, in principle, we can conjugate its numerator denominator at the very beginning because absolute value of the complex number and its conjugate are the same. So it is W of Z minus W of Z0 and W of Z bar minus W of Z0 absolute value. And since these two coincide, the logarithm equals to 0. So maybe it was, I don't know, maybe it was too much entailed, but now it should be clear that it is indeed a green function. So is it fine? So that.
Is there any straightforward way to find this function specifically, or
No. It's some art, I would say, to get conformal maps that do what you need. There are some questions like how to map a domain of this specific class to the upper half plane, or if they have more components, they should be mapped to some other domains, like to torus or to annulus. But for example, if you study domains with boundaries constructed from circles, it is a non-trivial problem. It is related to isomorphic deformations, Bernoulli equations, and all such things. So there is a lot of different questions related to those conformal maps.
Are the conformal maps useful for two-dimensional manifolds with boundaries?
Yes. Basically, in practical applications, people find conformal maps that map some interesting domains into upper half plane or something of this kind. So, because mm, I don't know what to say about domains without boundaries, like manifolds, like complex curves described as gluing of some pieces of paper. Such problems also exist in some questions about volumes of modular spaces of such surfaces, but I'm not sure if people are interested in the explicit formula that map such surfaces to some canonical forms. I don't know. So the typical problem has this form. So either to map some simply connected domain to the upper half plane, or some domain with several holes to, for example, upper half plane with several disks removed. And so there is a general theorem that any reasonable domain, any reasonable simply connected domain can be mapped to the upper half plane. And by reasonable, so the class of reasonable domains contains a lot of different things. For example, exterior of the Mandelbrot set can also be mapped to the upper half plane. So. And of course, our domains with cusps with non-differentiable boundary can also be mapped to upper half plane. So we will see such examples. And so what can be pretty easily proved, but I probably don't want to do this, that if we have a map from some domain, and then we perturb this domain infinitesimally, then we can adjust this map up to the first order in this perturbation. And this is enough to see that at least dimensions of all domains that can be mapped to this upper half plane oh, let me say like this. If there are domains that cannot be mapped to the upper plane, then codimension of this manifold is 0. Yes, and that any small deformation also leads to a domain that can be mapped to the upper half plane. Actually, I tried to tell this proof maybe in 2003, so you can find it in the lecture recording. So ask me in which lecture it was, but it was too technical probably. So I don't want to repeat it on this year. Let me draw this picture. The upper half plane. So let's consider this simplest example. Maybe not the actually it's not the simplest one, but an example of something that we have already seen. We want to map this unit disk to the upper half plane. And I guess is that this map is can be written as a fractional linear transformation. Well, this is Z, this is W. Z plus B over C Z plus D. So let's just try to guess it. So we want the boundary of this domain to map to a real line. So we want this expression to be real if Z is on the unit circle. So how can we do this? Let us try some formula like this. Actually, I forgot how to guess this formula in some simple way. Probably not this expression. Well, any such map is defined by a mapping of 3 points. So let us say that there are 3 points 1, minus 1, and I. So let's try to write an expression that maps 1 and minus 1 to minus 1 and 1. It maps I to 0 and maps minus I to infinity. So probably we just need to add. Let's check if it is fine or not. So W of 1, if it is written like this. So probably I need to add the factor of I here, and it should be fine. Yes, like this. So W of 1 in this case will be I times this. So it is minus 1. W of minus 1 is I 1 plus I 1 minus I. So it is 1. And yes, and W of I is 0. W of minus I is infinity. And there are points 0, 1, and minus 1. And this goes to infinity.
But the map is not necessarily subjective, or it's surjective?
It's subjective, of course. In a sense, we can compute the inverse map. So we computed this map for this 3 points, but we don't need anything else because the property of this fractional linear transformation is that they map circles to circles. And a straight line is a particular example of circle because of infinite radius. Oh, this is true because if you write an equation W times W star equals plus some linear combination of W's equal to constant. Well, let me write it somewhere like here. Yeah, I can erase this. So suppose that W satisfied an equation.
That we have to take a minus of that because it maps 0 to minus r.
No, but 0 here. Yes, thanks. You are right. 0. Yes, it's true. So let us think about the orientation of. Okay, I made another mistake here. So it was 1 minus I in the numerator. So it should be 1 minus I here. And it should be minus I here. So, but this is still minus 1, and W of minus 1 is what is it? Minus 1 minus I, or minus 1 plus I, but it should be 1. Yeah, thanks. And yes, 0 goes to I. And so in this particular example, there's a circle of radius 1 that maps to this real line, and but there is also circle. There are also circles in between. So the circles around 0 map to some shifted circles like this. No, so something of this kind. Yeah. And so I suppose that this W satisfied a second order equation, which can be written like this. This contains x squared plus y squared plus linear terms of W of z plus beta W star or bar. Let me use bar beta W of z bar plus gamma equals to 0. So if you substitute this fractional linear expression, you get this, and now we simply multiply everything by the denominator. So beta we have an equation of this kind, and now we can collect everything and get another equation that looks the same. A z z bar plus b z plus c z bar plus d equals to 0. So if you have so it is some circle with different radius, with different center, but it's still a circle. So if you want to solve some practical problem, if you want to map some circle into some straight line, you can simply map 3 points on the boundary of this circle using this fractional linear map to points you like, and it will be the map that solves this problem. One more remark is that if we study such maps with real ABCD, they form group SO2R, and this group preserves the upper half plane. It's a group of automorphism of this plane. So these conformal maps are defined up to the overall SO2R transformation. So we have more than one such maps. Oh, sorry. And also we should ask determinant of this matrix to be positive. So this is SO2 P, it's called PGL2 group. Maybe plus. So, are there any questions about this example? So let's study some different example, which is even simpler than this one. So let us study domain like this. With angle equal to pi over a. So again, we have u equals to 0. So it can be thought as a metal angle with 0 potential, because it is metal. And we are looking for gain function of Laplace equation in this domain. So can you try to invent a map that turns this angle into the upper half plane? So yes. Hmm? Yes, yes. And so this is z, this is w, and w z is z to power a. So we have this map, and the green function of z 0 is 1 over 2 pi logarithm of z to power a minus z 0 to power a over z to power a minus z 0 bar to power a. So it can be solved immediately. In principle, we could solve this problem using the normal modes because this geometry allows separation of variables. Because these boundary conditions are boundary conditions written in phi variable. So if phi is 0, our function should be 0, and if phi is pi over a, it should also be 0. So we could we could do separation of variables and construct this expression from normal modes. But this way it is even simpler. So a is 0, and we have this formula. But, let us compare this formula with another method for some special value of a. For example, let us take a equal to 2. So, for example, so we have a picture like this. And the function is on this expression. So you can write it as 1 over. Oh, let us write this here. Oh, absolute value. Sorry. So we have this expression. Do you recognize anything in this formula? Well, how could we obtain this in some alternative way? Yes, yes, precisely. Yes, and so we have indeed this quadrant which we are interested in, and we have a mirror charges. So suppose that we have z0 here. This is this contribution, and this comes with a plus sign. Then we have another charge at minus z0. This is in the opposite point. So it's here. Then there is a z0 bar, with minus sign. And there is so the 0 bar, and there is minus the 0 bar here. Of course, if you take some other rational angle like pi over 3, then it would also have the same interpretation, but there will be more different images. But for arbitrary, I don't know if it is possible to do like this. Probably not. So it was probably the simplest possible map, but it teaches us one lesson. And the lesson is that when this function that realizes the conformal map has such kind of zero, when it is z to the power a, then it turns an angle into a straight line. And I want to show you one more example when where this becomes important. So let us study this domain. And by the way, you may notice that this problem can be solved at least in one more different way, because if we have such kind of quadrant, we can also do a separation of variables, because we can perform a Fourier transform using signs in x and signs and in y, because these boundary conditions imply vanishing of functions of all functions on the boundary, but technically it would be equivalent to this reflection method, because each sign consists of two exponentials, and this combination of four exponentials, when you multiply them, would correspond to this four images. So it will be equivalent to the usual approach. Yeah. So let us study a domain like this. This is 0, this is phi I. And let us see what happens if you apply a map given by a hyperbolic cosine function. So this is C. So let us see what happens. So, no, yeah, probably it's fine. So first, what is the image of point 0? Yes. Uh, what is the image of this point? Pi I. And yeah. Thanks. And what is the image of this interval? Well, probably it's clear that it goes from 1 to -1, right? Hmm?
It's a continuous function.
Yes, it's cosine. It's cosine from 0 to pi. So you see that this part of the boundary maps to this interval from 1 to -1. And then uh, let's think about this boundary. So it goes from 0 to infinity. I have already raised this upwards for hyperbolic cosine, but it goes to infinity exponentially. So this line maps to this ray from 1 to infinity. So it is this domain. And the last part, of course, maps to another ray from -1 to infinity, because it is minus hyperbolic cosine. So, and the interior of this domain maps to the upper half plane. So you also see the same phenomenon as happened to this corner here, because when z goes to 0, uh, this hyperbolic cosine can be expanded as a Taylor series. And the same for I pi. Minus 1 plus x squared over 2 plus and so on. So there are these two corners that becomes straight two parts of a straight line. Yeah. So, but I am writing this example to show the same phenomenon with images that appears here. So, namely, let us write our green function. So, green function of z0 equals to 1 over 2 pi logarithm of course of z minus course of z0 we can also write it's a bit similar to this difference of squares because difference of two cosh functions is sinh times sinh. So we can write all this as Mm. Right. So there are simply such formulas. You can check them, or you can get them from a general argument that this function vanishes when z equals to z0 and when z equals to minus z0, and it is also periodic. So there is such an expression. Mm. And let us try to draw a picture of all contributions in this sum. Let us write all points where it has logarithmic singularities. Sorry, I should have placed absolute values everywhere, like this. So, so here is our domain. And suppose that z0 is located here. And this singularity comes with contribution plus. So since we have a sense of z minus z0 over 2, there will be another singularity with the same type of contribution shifted by 2 pi, by 2 pi I. So it will be in the next region. So we should jump by 1. So this will be z0 minus 2 pi I. And there will be, so there will be another singularity here. So this is a singularity of this first term. Then there is a singularity with minus sign here, and the whole series of the singularities. Minus z0. And here minus z0 minus 2 pi I. Here minus z0 plus 2 pi I. This for this expression. Then there is a simply z0. Sorry, this was plus sign. There is simply z0 bar. And I will not write the shifts explicitly. Hmm? Thank you. Yes, this is with minus. And yeah, it's also here. No, it's right here. And on the last term there is a minus 0 bar, so it's here. This minus also shifted, and this minus 0 is also no, sorry. Yes, it's here, and yeah, that's all. Yeah, so we see that this picture has so this configuration of charges is anti-symmetric with reflections with respect to this vertical line, which shows us that the potential created by them will vanish on the vertical line. It's also anti-symmetric, and it's also anti-symmetric with respect to any reflection with respect to this line or this line. So in principle, we could write this expression as an infinite sum of these charges, of contribution of these charges located at different points. So sum over okay. Let me write E in images. Chart of corresponding images over pi logarithm of z minus zi. Z0 like I. I's image of Z0 like this. And it is indeed true because there is an infinite product formula for the sine function. Namely, this formula tells us that sine of pi z is z times a product from n equals to 1 to infinity 1 minus z squared over n squared. Pi z like this. And it is oh, maybe I should have and this formula is actually not very far. I would say it is very close to this ideology, because if you want to prove that some expression is given by, for example, infinite product or infinite sum, we simply compare the analytic behaviors of these functions. So actually, the proof of this statement is slightly different. Almost equivalent formulation if it looks like this: that d in d z 1 over pi d dz log of sine of pi z, so pi z is tangent of pi z, and it should equal to sum over integer numbers maybe sum regularized in the appropriate way. Yeah. So to prove the statement, we can check that a residue of this of left hand side and right hand side coincide. So so it's cotangent. So we check that it is regular. For the integer. And second, its asymptotic behavior is is what we want. It should go to 0. Well, this statement is almost trivial because we can look at the asymptotics of cotangent around this around 0 and around any other 0 of sine, which is in the denominator, and it has residues with coefficient 1. Oh, so actually there should be 1 over pi in the right hand side, I think. Something like this. But the moral is that if you want to write any function, then it is more or less a product of z minus a position of all its zeros regularized in an appropriate way, so that this expression makes sense. Well, this series is convergent, of course, because it is n squared in the denominator, but there are more complicated cases. And this solution obtained from conformal maps demonstrates exactly this phenomenon. So comparing them, you can obtain a formula like this. And of course, this problem has another solution because you can perform Fourier transform on this interval. Using quantized sign function in the direction and simple sign functions in that direction. Okay, are there any questions about this? Okay, then thanks for your attention. Next time we'll study higher dimensions on the same equation.